What if I told you that in 10 quintillion years, the universe will be darker than the darkest night you've ever imagined? That's 10 with 18 zeros after it, a number so massive it makes the current age of the universe look like a fraction of a second. Want to take a journey to see what's left? Buckle up, time traveler, because we're about to fast forward through cosmic history at mind-bending speed. By the time we reach our destination, every single star you see tonight will be long dead, and the universe will have entered what scientists call the degenerate era. Sounds cheerful, right? Right now, our universe is like a bustling city at night, lights everywhere, activity buzzing. But here's the thing, stars can't burn forever. Even the longest living red dwarf stars, which can shine for 10 trillion years, will eventually run out of fuel. The last stars to form will be tiny red dwarfs, barely 8% the mass of our sun. These cosmic light bulbs are so efficient, they'll keep glowing long after everything else has gone dark, but even they can't escape their fate. When the last red dwarf finally flickers out, the age of starlight ends forever. So what's left after all the stars die? Meet the universe's most patient survivors, white dwarfs, neutron stars, and black holes. Think of them as the universe's collection of stellar fossils, except these fossils are still slowly changing. White dwarfs are like cosmic embers, the leftover cores of stars like our sun. Right after formation, they blaze at over 100,000 degrees, but by 10 quintillion years, they'll have cooled down to just a few thousand degrees. That's still pretty toasty, but compared to their starting temperature, they're practically ice cubes. Here's where it gets weird. These white dwarfs will eventually become something that doesn't exist yet, black dwarfs. No, not black holes. Black dwarfs are just white dwarfs that have cooled so much they don't emit any light at all. They'll be invisible balls of crystallized carbon and oxygen, floating through the darkness. But wait, what about those failed stars called brown dwarfs? These cosmic duds never got hot enough to start fusion, and by 10 quintillion years, they'll have cooled from thousands of degrees to room temperature or below. Imagine a ball of gas the size of Jupiter but colder than your refrigerator. Now let's talk about the universe's ultimate survivors, black holes. Stephen Hawking discovered that even these monsters slowly evaporate through quantum radiation. But here's the mind-blowing part. A black hole with 10 times the sun's mass takes 10 to the 69th power years to disappear. At 10 quintillion years, stellar mass black holes have barely started evaporating. The real giants, supermassive black holes with billions of solar masses, will take up to 10 to the 100th power years to vanish completely. That's a Google years. But here's a cosmic mystery that could change everything. Do protons decay? Protons are the building blocks of atoms, and if they're unstable, then all normal matter has an expiration date. Current experiments say if protons decay, they last at least 10 to the 34th power years. If protons do decay, every white dwarf, every planet, every speck of dust will eventually dissolve. The universe would become nothing but a thin soup of photons, electrons, and neutrinos. But if protons are stable, things get even weirder. Get ready for the strangest objects in physics, iron stars. If protons don't decay, quantum tunneling will slowly turn all matter into iron-56, the most stable nucleus. This process takes 10 to the 1,500th power years. That's a 1 followed by 1,500 zeros. But even they aren't the end. Given enough time, quantum tunneling will make them collapse into black holes. We're talking timescales so vast, they make our 10 quintillion year journey look like a blink. By 10 quintillion years, the universe is approaching what physicists call heat death. This doesn't mean everything is hot, quite the opposite. The cosmic microwave background radiation will have cooled to just 0.000000001 degrees above absolute zero. Space itself will have expanded so much that stellar remnants are thousands of light years apart. Imagine being so alone that your nearest neighbor is farther away than the width of our entire galaxy today. The universe becomes an impossibly vast, cold, and lonely place. Here's where quantum mechanics gets really weird on cosmic scales. At these ultra-low temperatures, quantum tunneling, the same effect that powers computer chips, starts working on entire stars. It's like the universe is playing the ultimate long game of atomic Jenga. Electrons will occasionally tunnel out of their atoms, even in solid objects. Over periods of 10 to the 65th power years, this quantum shuffling will reshape stellar remnants, making them perfectly spherical. The universe becomes a cosmic sculptor, working at the slowest pace imaginable. But wait, it gets even stranger with Boltzmann brains. These are complete conscious minds that could randomly assemble from quantum fluctuations. Imagine waking up with full memories of a life you never lived, in a universe where you just popped into existence. The Boltzmann brain problem is one of cosmology's biggest puzzles. If the universe lasts long enough, these random minds might outnumber real observers like us by an infinite amount. It's enough to make you question if you're real or just a cosmic accident with fake memories. Speaking of weird science, recent theories suggest something called generalized Hawking radiation. This means not just black holes, but all matter with gravity might slowly evaporate. White dwarfs could disappear in 10 to the 78th power years, way faster than we thought. What about dark energy, that mysterious force pushing the universe apart? It makes up 68% of everything, but we still don't really understand it. If dark energy changes over time, our entire timeline for the universe's future could be completely wrong. And don't even get me started on quantum gravity. When black holes shrink down to the Planck mass, about 0.00001 kilograms, our physics breaks down completely. We literally don't know what happens next because we need a theory that doesn't exist yet. The really mind-bending part, even in this cold, dark future, time still has meaning. Quantum processes continue, just very, very slowly. The universe might even create new Big Bangs through quantum tunneling after 10 to the 56th power years, a number so big it has over 50 zeros. So what have we learned from our journey to 10 quintillion years? The universe's future is darker and stranger than we can imagine, but it's far from boring. From iron stars to Boltzmann brains, from evaporating black holes to quantum tunneling on cosmic scales, the far future is full of mysteries. The universe at 10 quintillion years shows us something profound about reality itself. Even when the stars are gone and the cosmos is cold, the laws of physics keep working, creating new and bizarre phenomena. It's a reminder that nature always has surprises in store, no matter how far into the future we look. Want to dive deeper into the mind-blowing physics of the far future? Check out research from NASA, read papers on the RXE Physics Archive, or explore books like The 5 Ages of the Universe. Subscribe for more journeys through time and space. Who knows where we'll travel next? Until then, keep looking up and wondering what's possible.